Hi all. I hope you're having a good DPDK User Space Summit this year. A bit unusual, but due to the pandemic, but let's meet and talk about DPDK. So for the first part of the day, we had some talks about performance, throughput, latency, API design, and let's go dig into the debugging. So my name is Dariusz Sosnowski, and today I wanted to talk with you about debugging DPDK applications using RR. A little something about myself. In my professional work, I'm mostly interested in low-level systems programming, mainly networking applications and SDNs. For the last few years, Open Control, Tungsten Fabric. And for the last year or so, I have been working with DPDK applications. And outside of my professional work, for the last few months, I was getting to know RR as kind of a programming hobby. And from these two interests, one question arose: what has to be implemented in RR to support DPDK applications? So today I'm gonna walk you through what is record and replay debugging, how RR works, walk you through my initial research and work done so that DPDK applications can be debugged using RR, and then provide some next steps and summary of the current state. Okay, so regarding the debugging itself, in a traditional sense, we can debug the application using extensive logging, tracing, for example, eBPF traces, and also we can, probably the most of us has used some kind of interactive debugger, for example, GDB. Whenever you have an issue in your application, the error you're encountering, the root cause of it, normally it's not in the local area where you observe the error. So using the debugger, you just have to reproduce the error and then evaluate what conditions triggered this error. So for example, for some function f, you evaluate that a and b have to have some certain values for that error to happen. Then you run the debugger and application again, reproduce the first set of conditions, and evaluate again the next set of conditions for the function g. And then reproduce the second set of conditions, evaluate them, etc., and so on. This is a very iterative, error-prone process in some way. And here where comes record and replay debugging. So the basic idea is that you have a debugger which has a capability to record events which happen during application execution, store it into some trace file, and then using the same debugger without running the application in production environment, you can replay the trace and replace the events. So basically, whenever you have a trace recorded, you can just in the debugger progress to the error and just do the reverse step, go back to the previous instruction executed, or reverse to some previously set breakpoint, and then you do not have to evaluate. You can just see the conditions on which the error happened. All in all, record and replay debugging, I think, is a very useful tool. It can be less error prone to debug. It can save time, but at some costs, mainly performance, and the trace files can be really big. And some kind of errors are typically hard to record during application recording. There are a few available solutions. Mainly GDB has a support for process recording, RR, on which I'm talking today, and also Windows has its own flavor. Okay, so regarding RR, just to provide an introduction, RR is an abbreviation of record and replay. It is built on top of GDB and some Linux APIs, and it was built by Mozilla Foundation to deterministically debug Firefox bugs. Unlike GDB record, which single steps through an application and records the state before and after each instruction is executed, RR does not record each application instruction's effects on the application, but it assumes that whenever you have a program and it does not have any external side effects, then when you run it on a CPU, it will execute exactly the same. What changes the application behavior are the external side effects. For example, syscalls, signals, some specific instructions, or interaction with other threads and processes. RR manages to record these events using ptrace API, which it uses to record entries and exits from syscalls, catch signals, catch the specific instructions, for example, RDTSC and CPU ID. The one important thing about RR, it can also debug multi-threaded and multi-process applications, but it simulates them on a single core. It basically implements its own scheduler based around ptrace API and hardware performance counters. Just to reiterate, so that we have a shared view of the limitations of RR, as I said before, it simulates a single core machine. Not all syscalls are supported, which I'll talk more about on later. And RR does not properly record application behavior where applications share memory with processes or devices, in case of DPDK, which are not recorded or directly observed by RR. Okay, so now I would like to walk you through my initial research and work done on debugging some simple DPDK applications. So here are some of my test assumptions. Most of my research work has been done using Mellanox cards with their DPDK PMDs and Virteo PMDs. If you want to know little detail, if you would like to know more detail about this setup, please feel free to ask on chat or after the talk. Okay, let's start with something simple. Let's have an application that initializes the DPDK abstraction layer, waits until this isRunning flag is set to false, then perform abstraction cleanup. This isRunning flag will be set to false whenever we receive a SIG signal. So, for example, where someone clicks Ctrl+C. So, as you can see, out of the box, I did not expect any result better than this. RR crashes because it encounters syscalls which it does not have any implementation for handling during recording. In this case, it's IOPL syscall. So through my research, I have found that in the abstraction layer, there are several syscalls which are needed to support. The one IOPL, which I mentioned. The second is that the Mellanox PMDs depend on IBverbs library, which underneath use RDMA verbs IOCTL commands heavily, and also some missing ETH to IOCTL commands had to be implemented. All these specific syscalls have to be properly handled in the RR syscall handling mechanism. And I would like to walk you through how it does it. So imagine an application which runs an IOCTL syscall. It takes a file descriptor and the IOCTL command type. And also for some IOCTL syscalls, we are passing a buffer to the syscall. In case of Mellanox PMDs, it is the InfiniBand command vector, let me put it this way, which is a variable length structure. So depending on configuration of the application, depending on its execution flow, this parameter can have different lengths. Also with each syscall call instruction, we have some register values connected to it. So whenever the application enters the syscall, RR stores the register values using ptrace API in the trace file, and then records the address and length of a buffer or buffers passed to the syscall. Whenever application exits the syscall and application receives its return value, RR records the resulting register values, register contents, and also stores the previously recorded buffers contents into the trace file. After integrating these syscalls, which I mentioned before, in the RR syscall handling mechanism, the abstraction layer initialization application runs just fine. So let's move a little bit closer to the working production application. Let's imagine an application which has initializes a single port with a single queue, and whenever we receive a packet, we hex dump it on the standard output. So here is an output of this simple application. We can see that we have configured port 0. We are running our worker lcore, and we receive some packets, hex dump the contents. The application is stopped at SIGINT signal, and at the end of running of the application, we print out how many packets were received. With this syscall's implementation for syscall handling in place, application recorded just fine. But during the replay, application hanged indefinitely. The reason for that is during a replay, it has a series of events recorded, for example, scheduling events or syscall events, and RR expects them to happen on a specific point in time. But because it does not record shared memory, application logic might not end up at the specific event at a specific point in time, but also it may never happen. In this example, where we have our application, and in more general view, we have an application which each lcore interacting with its own Rx or TX queue. We have an lcore interacting with a mempool which is shared with secondary process. These queues are also populated by the NIC, and also interfaces with syscall. These all memory interfaces are observed. These all memory operations, memory interfaces are observed during recording. The application receives the correct results. But during replay, since we do not record what happened in the memory, in the shared memory, what secondary applications and NIC has done is not replayed. So let's try out some heuristic solutions. One which came to mind is that DPDK supports interrupt-driven packet receiving. So let's provide some synchronization mechanisms on these interrupts. There is one specific use case where RR handles shared memory usage between processes, process which is recorded by RR and the process which is not traced by RR. But in this case, the limitation is that this memory has to be read-only. So I extended this mechanism to support read and write shared memory and introduced synchronization points into my application. So the heuristic solution basically works like whenever we exit from the epoll, which waits for the receive interrupt, we store the huge page contents in a trace. And whenever it happens during a replay, and we record these epoll events, and during a replay, whenever we emulate the syscall in RR, we restore the huge page contents. This is the output of the program, which uses receive interrupts to do this. It's basically the same as the app I showed before. It configures the port, hex dumps the packets. As you can also see, despite printing the packet contents and that it received the packet, it also shows that the lcore was woken up by an interrupt. Application is ending with a SIGINT, just as before. With this heuristic solution in place, the application recorded just fine, and during a replay, we can see that for very, very low PPS rates, the application behaves just as expected. We also have the replayed signal received by a process, and the application finishes just the same way. We can go back in time, debug, inspect everything. So let's increase PPS size and see what happens. It will possibly be a bad idea because this heuristic solution is not very correct in a sense because there are some time synchronization problems which happened during when I increased the PPS rate. So, for example, in this example, I removed the hex dump logs, and we can only see when lcores are woken up. During normal execution, without the overhead of recording and storing the memory page contents, we can see that for each packet received, there was one wake up. But during during recorded execution, we can see that there were less wake ups than the packets received. There is some overhead during reading memory from the device. And whenever we try to replay it, we can see that the observed behavior of the application mismatches the behavior of the application during replay. What happens is that whenever we try to increase the PPS rate, the more things can happen and the more memory changes between the interrupts we handle. So in this timeline, we can see that our application calls equal wait syscall to wait for applications. It is put back to sleep by the kernel. Then asynchronously from that, the NIC receives a packet and performs DMA writes to the application memory. And after that, it triggers an interrupt, which in turn wakes up our application. Before we start receiving packets, we disable interrupts, and then the RX burst method in DPDK API reads the memory and polls the descriptor queue so that it can get the received packets. But during the call of this method, the NIC can write another packets to the memory, and still the RX burst method will return that it received 3 packets. But during recording, RR saves the memory state on the interrupt. So this packet received is recorded and observed, but during replay, since we do not introduce any synchronization points in this time span, these packet receipts are not observed. And as a result, the application done less work, and then we have this consistency mismatch between the performance counters during record and replay. So the proper solution would require some kind of kernel or RR or hardware mechanism so that we can store in the recorded trace, we can store all observed memory reads. We can observe what application has seen in the memory. Preferably, it will be what is required is that we can only see the memory read by the application at the time of read. Not at the time when the change in memory happened, because we only care about how application behaves. This type of mechanism is not currently supported in RR, but I managed to give a shot with one of the oldest tricks in the books in the debugging. So basically implement segmentation fault intercept. So the basic idea is that whenever you would like to implement a memory breakpoint, you would change the memory protection so that the application cannot read to or read from or write to it. And then in a debugger, we handle the segmentation faults by changing protections back to read-write, single-stepping through an application, and disabling read-writes on this memory. In the case of DPDK applications, we can safely assume that each huge page is the memory we have to observe, and it is done for every huge page. And some initial results are pretty underwhelming because this type of memory synchronization mechanism introduce 1,000 times slowdown even for a simple application which just initializes and cleans up application. It also introduces some correctness issues for the replayed application, because not only we have to single step, we have to handle each segfaults, but we also have to handle syscalls differently. Some of the syscalls will, as parameters, receive pointers to buffers, which are now kernel will be unable to read from or write to it. And to be honest, it's still work in progress. I did not manage to have a working POC of this type of solution. So investigating the next steps for the usage of RR with DPDK applications. First of all, some of this work is ready to be open sourced, mainly on support of the syscalls used during initialization. There are a few. There's one question from Anurag: would hardware-based memory watch aid in recording snapshot whether a huge page is written? You're talking about hardware-based watch point, for example, like in GDB. Good question, actually. So for example, we would have to know the addresses which the application accesses. So as far as I know, Yes, that's correct. There's a very limited number of hardware watches. So to set up these watch points, you would need to know addresses which application accesses, and then set up these watch points. So it would, for RR, it would require some pre-processing of the application, possibly some instrumentation, and then managing this set of watch points. Yes, but the Anurag said that we know the huge page, that is what DPDK reads writes to. I'm not sure how hardware watch points works, but if you know if they can be triggered by an access to a memory range, it would possibly work. But from what I understand, they work by access to the specific address. Okay, so yeah, if they can take start and end addresses, it could work. There's one question from Stanisław. How would this recording method work for applications which deliberately try not to perform syscalls, as those introduce undeterministic delays? So first of all, this is the one of the trade-offs of using record and replay debuggers. You have to let's do order. You will lose some performance, mainly in the throughput and in latency. Since RR emulates the single core machine, your application will run slower. But when an application does not perform any syscalls, there are other synchronization points we can utilize to store the memory contents. Because RR does its own scheduling, it also records the events on records the points in time when the application is being scheduled and when it is being yielded for another thread. We can track memory on these scheduling events. One of the solutions which I would like to research and probably provide some proof of concept of working is double buffering. So whenever a huge page is mapped into RR, whenever a huge page is mapped by a DPDK application, we map it to RR and to the DPDK application. Then through emulating reads from page map, we can instrument the application so that the NIC will write to RR's memory instead of application memory. And on the synchronization points, for example, scheduling, we can get the contents from a buffer in RR and forward it to the DPDK application. And it will probably result in undeterministic latencies, and there will be some work need to be done to make it deterministic. Mainly, I'm concerned here about the latency, but it is some work to be done and area of research. Another solution which is very interesting, in my opinion, is that Linux kernel allows. Okay, thank you, Konstantin. Just a reminder, there's another session to be started in 1 minute. Okay, so just to summarize, a quick summary. Out of the box, RR does not support DPDK applications. There is some work to be done. During the research for this presentation, I implemented some of the syscalls which are required during initialization and cleanup of DPDK. But recording observed memory changes is still an issue and is hard. And I believe and I hope that in a few months' time there will be a working solution for that. Okay, so thank you all. I think I see that you are going to the next session. Thank you very much.